In this video, we're going to expound on what we talked about last time with dilations. Remember that dilated figures are where we take a pre-image and we either enlarge it or we shrink it to an image. Let's talk about some of the features that happen when we dilate a shape. Remember that the corresponding angles between our figures should remain the same size. Just because I shrink down a triangle doesn't mean my angle shrink down. Because we don't have any angle degrees marked here, we can use tracing paper to test whether the corresponding angles are indeed congruent. So let's check out angle R here. Do I have an angle over here that matches angle R? Okay, that doesn't seem to fit. It looks like angle R and Y match up, so we can mark them. Angle R is congruent to angle Y. I'll use one tick mark to denote that they are congruent. Let's check out angle P. Looks like angle P matches up with angle X. We'll use two tick marks to show that angle P and angle X are congruent with each other. Okay, let's check out the last one. T does indeed match up with W, so the angle T is congruent to angle W.
So one property of similar figures is that the corresponding angles have to be congruent. Another property of similar figures is that the corresponding sides have to be proportional. So let's first figure out which side correspond to which side. So if you look at our big triangle here, we can see that this side, 18, is our longest side. So that means that this has to correspond with the longest side on this triangle. 18 has to correspond with 12. Now let's look at the smallest side on this big triangle is 12. So 12 has to correspond with 8. So that means that 15 has to correspond with 10. Now that we know which sides correspond to each other, we have to see if these sides are proportional. Now remember, proportional means that these fractions should be equal to each other. 18 divided by 12 is going to give me 1.5. 12 divided by 8 is going to give me 1.5. And 15 divided by 10 is going to give me 1.5. So since each of these fractions are equal to each other, it means that these sides are proportional. So this 1.5 right here, this is our scale factor. And if you remember back to our last video, our scale factor tells us, well, what do we have to multiply each side by to get the new side length of our new dilated shape? So in our last video, we talked about how if our scale factor is greater than 1, it means that our shape is growing. So this scale factor is taking each side length of the smaller shape, multiplying it by 1.5, and then getting the resulting larger shape. In this case, this is my pre-image, and the larger shape is my image. If I took 8 and multiplied it by 1.5, it's going to give me 12. If I took 12 and multiplied it by 1.5, I'm going to get 18. If I take 10 and multiply it by 1.5, I'm going to get 15. So what if this was my pre-image and this was my image? How would that change my scale factor? So now if I said 15 times 1.5 is not going to give me 10. So 1.5 is not my scale factor if I'm going from the larger shape to the smaller shape. So to figure that out, we just have to flip each of these fractions. So instead of doing 18 over 12, we're going to do 12 over 18 and 8 over 12 and 10 over 15. If we solve each of these fractions, 12 divided by 18 is going to be 0.66 repeating, or leave it as 2/3. In derivative, if your decimal is repeating or is going to go on forever, you have to write it as fraction because derivative won't accept the rounded decimal. 8 divided by 12 is 0.66 or 2/3, and 10 divided by 15 is 0.66 repeating or 2/3. So my scale factor, if I want to go from larger image to the smaller image, is going to be 2. And that makes sense because this scale factor is less than 1, which means that I'm taking my pre-image and I'm shrinking it.
All right, let's check out this example here. We've got two triangles. We want to know, are they similar? We know that corresponding angles between dilated figures should be congruent. We also know that the sides are proportional. We're not giving any sides right now, so we need to look at just our angles. If I look at 60 degrees right here, does that have matching congruent angle on this side? Okay, I got 25. That doesn't quite work. 30, no. I can use my properties of triangles to find out what's missing here. If you remember, triangles add up to 180 degrees. 180 degrees looks like 25 and 30 add up to 55. So I can subtract 55 degrees to find out how many degrees are missing here. So 180 minus 55 is 125 degrees. So we know that this missing angle is 125 degrees. 60 does not correspond with any of these angles. None of these are also 60. So we know that these are not similar figures because the corresponding angles are not congruent. So we know that these are not similar just because there are no corresponding angles that are congruent, which holds the shape. Even though the angles are proportional, we only care that sides are proportional with similar shapes.
All right, in this example, we are given that these two figures are similar, and we need to write a similarity statement. All right, so we're going to take this first figure here, and we can write it in whatever order we want. I'm going to write it as LOVE because that spells love. So we know that figure LOVE is similar to this figure. We need to make sure that the order that we write these letters corresponds to each of these letters. This angle L is a right angle, and it's also connected to this longest side right here. So let's figure out which one is our right angle that's connected to the longest side. We see that D and C are right angles, but D is connected to this longest side. So D is going to correspond with L. O is a right angle connected to the shorter side, and C is a right angle connected to the shorter side. So C and O are going to correspond. So in this first figure, I went LOVE, and over in this figure so far, I have D, C, and to keep that same flow, I'm going to then go to B and then to A. So when we write a similarity statement, we can pick wherever we want to start, but we need to make sure that we flow. So if we start at L, we go O, then we need to go V and E. We can't go LOEV. On your derivative assignment, you may be given a similarity statement that looks something like this. You have to determine if the side lengths are proportional. Because we know that these two shapes are similar, if we're given side length LO, we know that has to correspond to side length DC. Because in our similarity statement, LO and DC are in the same spot. And with similar figures, we know that each pair of corresponding sides has to be proportional. And we know that proportional means that they have to be equal to each other. So if LO and DC correspond, we could say that VE corresponds with BA. And that has to be equal to this fraction here. What if we said side length OV corresponds with CB? So OV corresponds with CB. And let's say that's equal to AD. Because if we look over at this shape, that's saying AD right here, this side length here. AD corresponds to EL. We have to figure out, is this a true statement? Well, OV over CB, that's the middle piece here, and AD and EL is the end pieces. So that is true. But notice the top of this fraction is from this figure, and the top of this fraction is from this figure. In order for this to be true, we have to be consistent with how we write this. We'd have to switch one of them. So we could say OV over CB is equal to EL over AD. We just have to be consistent with which figure we have on top and which one we have on bottom. So this statement is not true, but this one does work.
Here we have some pre-written proportions here, and we want to know, is it always true? So we got VE, and does that correspond with BA? Okay, looks like VE are the last two letters here, and they do correspond with BA, so that looks good. OV are the middle two, and CB are also the middle two, so we know that they are correspond with each other. And then we want to check across the fractions. VE is on this side, and OV is on this side, and BA and CB are both from this side. So we know that this is always true. Looking here, we got DA and LE. DA are the first and fourth letter, and we're coming over here to the first and fourth letter. So these are corresponding sides. Let's look at VO and BC. VO and BC. Okay, they do correspond with each other. That's great. And then we want to look across. So DA goes to LE, and VO goes to BC. So we see that this top half of our fraction, they're not coming from the same figure, and the bottom half are not coming from the same figure. If we flip this, then it would work. But in this case, it doesn't work. Let's look at this one here. We got DC, first two letters. Does that correspond with LO? Yes, it does. BA corresponds with VE. Oh, looks like we got EV, which is backwards because this is the third and fourth letter are put first. And so we need the third and fourth letters. So this should be VE. So if this were just switched, then that'd be fine. But because it's not switched, we know that this is not a true statement as well. A common problem you will see is you are given two similar figures and you want to find the missing side length. We know that corresponding sides are proportional, which means we know we're going to be creating fractions between our corresponding sides and try to solve for our missing side. So we want to solve for x. We see x here is extended between this angle marked here and this angle marked down there. We know that x will also have to run from this marked angle and that marked angle. So finding that over here, we see that x corresponds with 8. We know that x corresponds with 8. I can write that as x over 8 or 8 over x. Let's say x over 8. Going from this to this. So we got x over 8. Now I need to figure out what corresponds with 10. We got 10 here. Since x and 10 are opposite sides of each other, I know that the same thing's going to happen here. 8 and 6, mostly opposite of each other. So we know that 10 and 6 have to correspond. I don't want to write my fraction though, because I started off on this fraction, x to 8. I have to keep that same flow. I go from 10 to 6. So we're going from 10 to 6. Now we got x over 8 equals 10 over 6. Remember, with our undoing method, we want to undo whatever's with x. X is being divided by 8. So to undo a divide by 8, I'm going to multiply this side by 8. And whatever I do over here, I gotta do over here. Multiplying this side by 8, or 8 over 1, gives us a giant 1. 1 times x just leaves us with x. So that goes away. And then we're left with 10 over 6 times 8. Remember, 8 is the same as 8 divided by 1. 10 times 8 is 80. You know, 6 times 1 is 6. We can leave it as 80 over 6, or we could simplify it down to 13.3 repeating. In derivative, you are not able to write 0.3 repeating, like input it, so you would want to write the fraction form in order for it to be most accurate. In middle school, you may have learned another method for solving proportions, where instead of just undoing the one side like we did here, you undo both sides. If I want to undo a divide by 8, I'm going to multiply by 8 on both sides. 8 over 8 is just a giant 1. Since I undid the fraction on this side, I could undo the fraction on this side. Opposite of dividing by 6 is multiplying by 6. So divide by 6 and times by 6 gives us a giant 1. Since I multiplied by 6 on this side, I have to multiply by 6 on this side. If you kind of see here, this this 8 ended up multiplying here, and this 6 ended up multiplying here. We can see here that we ended up with 10 times 8, which is just the same as doing 10 times 8 across here, which is 80. And then here we ended up with 6 times x, which is, if we just shortcut it or jump to this, we just do 6 times x. And then to undo it times 6, we divide by 6, and then we're left with the same answer that we got from before. This method you may have heard of as butterfly or cross multiply, but it comes from the idea of just undoing both fractions. And when you undo both fractions, you are left with giant ones, and then you end up multiplying this denominator with this numerator, and you end up multiplying this denominator with this numerator.
We're going to use what we just learned in our last example to see if we can solve for this missing side x. First, we have to decide what sides correspond with each other. So let's look at our similarity statement here. We know that triangle ABC is similar to triangle PQR. If we look at the first two letters of our similarity statement, we can see that side length AB right here corresponds with side length PQ, which is right here. We know that 5 and x are going to correspond with each other. So I'm going to write it as 5 over x. And because I started with 5 on top here, that means my second fraction has to have this triangle be on top to stay consistent. All right, and the only other side length I have on this triangle is BC. Even though I have 2 side lengths over here, I have to figure out which one corresponds with BC. BC, if you look at our similarity statement, is the last 2 letters. That means it corresponds with QR, which is right here, side length 9. We can say that 5 over x is going to be equal to 6 over 9. And again, because I had 5 on top here, 5 is in this first triangle, I need to have 6 on top in my second fraction. Now let's see if we can solve for x. So if we remember what Tiana taught us in our last example, if we undo both sides, we can figure out what x is. Because x is on the bottom here, if I want to get rid of this fraction, I can multiply this side by x, and then I have to multiply this side by x. And over here, x divided by x just becomes 1. The denominator here is 9, and if I want to get rid of this fraction, I can multiply this side by 9, and 9 divided by 9 becomes 1. Then I have to multiply this side by 9. So I'm left with 5 times 9, which is 45, and that is equal to 6 times x. So if we rewrite this, we can use our shortcut with cross multiplication, which is when we multiply across the equal sign. So this denominator gets multiplied by this numerator, and this denominator gets multiplied by this numerator. So I'm left with 5 times 9 is 45 equals 6x. So I'm left with the same exact thing. So if you guys want to use this shortcut, you can, or you can use this method by undoing both sides. Either way will work. Our last step here is if I want to get rid of this times 6, I divide by 6, and I could do the same thing over here. 45 divided by 6 is 7.5. And so when you guys write this in derivative, you can leave it as 45 over 6, or since this decimal doesn't go on forever, it ends here at the 5, you can write it as 7.5 because that is an exact answer. So either of these would be acceptable.
All right, we got one more example for you guys. In this case, we want to solve for x and y, and we know that these two shapes are similar. So let's find some corresponding sides. So we see that 18 corresponds with y minus 4. I can write that as 18 over y minus 4, or I can write it as y minus 4 over 18. Doesn't really matter which way I go, just as long as my second fraction matches it. So we'll do 18 over y minus 4. I see that x corresponds with 11, but if I have 2 unknowns and only one equation, I'm not able to solve this. I would need another equation to help me solve for this. So I need a different side. We see that 24 corresponds with 8. So we can say 24 over 8. Going over what Emma was sharing with us on our shortcut with cross multiplying, I can do 18 times 8 because I know that if I undid this fraction, it'll just end up on top multiplying with 18 anyways. So 18 times 8 is 144, and then that is equal to, and then we know that y minus 4 is going to end up being multiplied on top with this numerator here. Since I know y minus 4 is all being multiplied by 24, I'm going to be very careful to use parentheses to help separate my multiplication. So I know 24 is being multiplied by all of y minus 4. All right, from here we want to tell the story of y so we can get y by itself. What is happening with y? There's a couple ways we can go about it. We could either rewrite this whole side using the distributive property, or I could undo a times by 24 by dividing both sides by 24. It's probably easier to divide by 24 first than to distribute and make more work for ourselves. So we're going to undo a times by 24 by dividing by 24. Whatever we do this side, we're going to do over here. 24 over 24 is a giant 1. I'm left with y minus 4 equals, and 144 divided by 24 is 6. Last step to get y by itself, y has a subtract 4. To undo a subtract 4, we are going to add 4. So I'm going to add 4 both sides, and I'm left with y equals 10. So I know that this side is 10 minus 4 because y equals 10.
So now let's see if we can figure out what x is. We now know that this side is 10 minus 4, which is 6. So we could use this side if we want to. First, let's figure out what side corresponds with x. Well, x corresponds with 11. So I'm going to write that over here. X over 11 is going to equal. Now I have a choice of sides. I could use 24 and 8, or I could use 18 and 6, because now we have this side here. So I'm going to use 18 and 6. X over 11 is going to be equal to 18 over 6. Because I have x on top here, I need to make sure my 18 is on top in this fraction because 18 and x are in the same shape. So now I can use my cross multiplication to solve for x. X times 6 is just 6x, going to equal 11 times 18, which is 198. And so then I can do my last step of solving for x by undoing the 6 here. To undo a times 6, I have to divide by 6 on both sides. So I'm left with x equals 33. So now that we have found our two missing sides, we can check the scale factor and see if we can figure out what that is. So if we start here with this smaller shape, we want to figure out how much bigger is this bigger shape. What do we have to multiply each side of this smaller shape to get this shape right here? Well, to get from 11 to 33, I'm going to have to multiply that by 3. To get from 6 to 18, I'm going to have to multiply that by 3. And to get from 8 to 24, I'm going to have to multiply that by 3. And if it wasn't as easy to see with the numbers that we're given, we can also use proportions. If we want to figure out how to get from the smaller shape to the bigger shape, then I need to take whatever number I have in the bigger shape and divide it by the number in the smaller shape. So I could say 24 divided by 8 is going to be equal to 33 divided by 11, which is going to be equal to 18 divided by 6. And all of these are equal 3. So my bigger shape is 3 times bigger than my smaller shape. So 3 is my scale factor that takes me from this smaller shape to this larger shape. And if I wanted to find the scale factor that took me from the larger shape to the smaller shape, then I would just flip this. And I would say 8 divided by 24, which is going to give me 1/3. So it's telling me this smaller shape is 1/3 the size of this larger shape. So the scale factor from the bigger shape to the smaller shape is 1/3. And that follows this over here, where if my scale factor is larger than 1, my shape is getting bigger. And if my scale factor is less than 1, my shape is shrinking. And if you notice here, our scale factor here is 3, which is the same thing as 3 over 1. And then our scale factor for this one right here is 1 over 3. So another way we can find the scale factor for going the other way is just taking the scale factor that we have and flipping it. So instead of 3 over 1, we're going to have 1 over 3.